Anybody come up with two-step synthesis? Sorry, so this is your very first exposure to multi-step synthesis, right? And this is one of the, I would say this is one of the things to get excited about in chemistry, right? Where you can take a molecule, take it through several steps, make many changes to that molecule, right? And make something functional, make something different. In order to do synthesis, you have to think a couple of steps ahead, right? Or you have to think about all of the different reactions that you've learned so far. Okay. So first of all, let's talk about why we can't take a carboxylic acid and make an amine in one step, right? So we learned about substitution of a carbonyl. We drew out this really simple scheme to show how that substitution typically occurs. Right, so that substitution, all we're doing is taking a leaving group, right, which is X, and we're replacing that leaving group with a nucleophile, which in this case is Y. Right? And functionally how that works, or mechanistically, right, we're going to take Y, add to the carbonyl, break the carbon-oxygen pi bond, form a tetrahedral intermediate, and then in the second step, kick out the leaving group, kick out X, right? So we have our products, and this reaction is reversible. Right, so if you look at where we want to start and where we want to end, right, if we go by this mechanism or this scheme, right, we should assume here is our electrophile. The benzene ring portion of this carboxylic acid, I'm just abbreviating as AR for aryl, right? So we don't have to draw it out. Okay, and you can see I'm trying to put a new group onto that carbonyl, which is an amine, right? So according to this scheme, I should just add the amine, right? What's wrong with this reaction, or what's going to happen in this reaction if I mix these two things together?
The amine is going to take the proton off of the alkyl group.
Great, right? So carboxylic acids, unlike the other carboxylic acid derivatives, has a primary reactivity of being acidic, right? Rather than things adding to the carbonyl carbon, right? These nucleophiles or bases are going to pluck the proton first. And amines are pretty good bases, so we would expect this amine to pull the proton. And that's going to give us an ammonium salt, right, or ammonium cation. So this is a nitrogen without any lone pairs, so it's no longer a nucleophilic nitrogen, right? And it's also going to give us the carboxylate anion, right? And this carbon, because we have electrons flowing through that carbon to stabilize the electron pair through resonance, this carbon is no longer electrophilic. Right, so what we did was we tried to take an electrophile and a nucleophile, mix them together, right, so that they react through substitution, but when we did that, they acted like an acid and a base, right, in a predictable way, right, we should be able to predict that. Okay, so that's why we can't make amines in one step from carboxylic acid. It's not through just the regular carbonyl substitution. Right? Because we can't tell our reagents how we want them to react. They're just going to react the way they do. Questions about this? Right, so what that means is that if we can't mix amines with carboxylic acids, right, to get to an amide, that means we have to turn this carboxylic acid into something else first, right, and then turn it into an amide. Right, so what could we turn that carboxylic acid into first that we can further turn into a carboxylic into an amide? So you only know a limited number of reactions, right? So you only know a few things that you can make from carboxylic acid. The hydroxy group? Yeah. So I mean that's what you want to do, but you can't just say leave as water, right? There has to be something to substitute it off. So what other functional group would you be making?
An ester?
An ester, good, right? So we learned from that big conversion chart of the carboxylic acid derivatives that any more reactive carboxylic acid derivative, we can make the less reactive carboxylic acid derivatives, okay? Esters are going to be more reactive, better electrophiles than amides, so we can take an ester, treat it with an amine, right, and form an amide. So, if we're going to make an ester, we might as well just make it a simple ester, since it's a synthetic intermediate that we're not going to hold on to. Right, so here's my carboxylic acid. Starting material, right? And then here's my ester product. Right, so the first product in this two-step synthesis. What am I adding to this reaction to affect this transformation?
Catalytic PTSA and then ethanol.
Excellent, right? So catalytic PTSA, catalytic strong acid, ethanol, right? And then we'll do something in this reaction to get rid of water. So we can go into the lab and actually do it, right? A couple of things that we can do to favor the product is we could put in a bunch of ethanol, right? A bunch of the nucleophile. We can run this reaction in a Dean-Stark trap, right? And there are other chemical ways of also getting rid of water. You can add drying reagents to the reaction. Right? Does anybody remember what the name of this reaction is?
Fischer esterification.
Yeah, Fischer esterification, right? So a lot of these reactions, they were discovered by a bunch of old stodgy German chemists, right? So they've been named after those German chemists. The names, you can know them, you don't have to know them, it doesn't really matter. I would say Fischer esterification is a common enough reaction that it's good to know the names, just in case somebody tells you to run a Fischer esterification in the lab. All right, once we have this ester product, right, we can run this reaction, do a workup, isolate this product, right, and then we set up a second reaction. What's going to be in that second reaction? Not an alcohol, right? So you're losing the alcohol, or the alkoxide, as we do. So in this case, you just want the amine, right? So if you look at what amine we want, on this nitrogen there needs to be an allyl group, right? So this 3-carbon piece with the double bond, and then a methyl group. So that's the amine that we're going to be adding to this reaction. Questions about this?
In the lab, will this be taking place all in the same place?
On the same flask? No, yeah. So this is going to be a two-step reaction. So in this case, you would have to actually run two separate reactions, right? So you would run this first reaction in a round bottom. When the reaction's over, you would do the workup in the subfunnel, right? Isolate and purify as much as you can until you get to this, rotovap down, and then use this in a brand new reaction, right? Set up a whole new reaction, a whole new round bottom with brand new reagents.
So would you want to keep a catalyst in for the second?
You would not, you would not. And so the workup, right, when you do a workup of this reaction, you're likely to do a basic workup, right? Because the base is going to react with this acid, bring it into the water layer, and you're going to be left with just your acid. Other questions? All right, so I want to just really quickly return to where we left off on Wednesday, where we were talking about the relative electrophilicity of the different carbonyl compounds, right? And so what we were talking about, right, the thing that makes electrophiles, electrophilic, or carbonyls electrophilic is this pi star orbital, right? So the pi star orbital on carbon, that's where the nucleophile, and that's the orbital that the nucleophile is reacting with. Okay, so that's the pi antibonding orbital, right? And there are two things that can stabilize that pi antibonding orbital, right? So that really what we're looking at is if this pi antibonding orbital can get electrons or get some electronic satisfaction from groups within the molecule, then it's not going to be as electrophilic or as reactive with nucleophiles outside the molecule, right? And so the two elements that we pointed to that can help stabilize that pi antibonding orbital or help stabilize the electronics or the electrons in the system, one is going to be hyperconjugation from a nearby sigma bond. Right, so we use that to rationalize the difference in electrophilicity between a ketone and an aldehyde, right? We said that ketones, because they're two carbon groups, is going to have two elements of hyperconjugation, right? Whereas an aldehyde with only one carbon group will only have one element of hyperconjugation. So the ketone should be more stabilized, right? That pi antibonding orbital should not want electrons as much in a ketone as it would in an aldehyde. Right, questions about that? Everybody's clear? Remember that from the other day? Okay. The other element that we pointed to that can stabilize the empty orbital or make that antibonding orbital less electrophilic is formal conjugation. Right, so this happens whenever you have a heteroatom with a pair of electrons, so something like oxygen or nitrogen attached to the carbonyl. Right, that element, that atom is going to be sp2 hybridized, so a pair of that atom's electrons are elevated to a p orbital and can overlap with the pi system. Right, so if you have electrons from an attached heteroatom resonating or being conjugated with the pi system, right, then this pi system doesn't want as much electron density from an outside nucleophile. Right, so these are the two elements that help us stabilize or make that carbonyl less electrophilic: hyperconjugation and formal pi conjugation. Right, and so we also talked about the ester and the amide, right? Esters are going to be less electrophilic than ketones because of the conjugation where you're formally putting electrons into the pi system. That's going to have a much greater effect, right, than hyperconjugation. So as a result, esters are less electrophilic than ketones. And then we talked about amides and said that when this X is oxygen, oxygen being more electronegative won't give as much electron density to the pi system. Nitrogen being more electropositive, less electronegative, right, is happier with its electrons farther away, picking them up more easily. Questions about that so far? So that was just a review, right? We just went over aldehydes, ketones, esters, and amides. Yeah.
So you're saying that an X group that contributes protons to the pi system,
Not protons, electrons.
yeah, electrons to the pi system of the carbonyl group
Mhm.
are going to be more stable.
It's going to have a greater effect on the electrophilicity, yeah, than just hyperconjugation.
Okay.
And that, I mean, the reason why I say that is because we can see that here, right? Here with the ketone, you have 2 elements of hyperconjugation. With the ester, you would have 1 element of hyperconjugation and 1 element of formal conjugation. And so that direct comparison shows us that the formal conjugation is often much more effective. Other questions? Right, so that leaves us with trying to explain why we have such a high reactivity on acid anhydrides and such a high reactivity on acid chlorides. Right? Part of the reason why the reactivity of these is so great is not necessarily because the energy of the starting materials is so high, right? But because the energy of the products is so low. You look at the leaving groups on these molecules, right? On one of them, the leaving group is a carboxylate ion, right? So negative charge on oxygen that's stabilized through resonance, right? The other one, the leaving group, is a chloride anion, which is a pretty stable, right? Big, fuzzy, polarizable anion. Okay, so some of it has to just do with the low reactivity, high stability of the products. Okay, on the acid anhydride, if you look at this, right, kind of ignoring the carbonyl, if you look at this, it looks like the ester, right, but it's much more reactive than the ester, right? So why would this carbonyl be more electrophilic than this carbonyl? Both of them have oxygen next to them, right? In both cases, that oxygen with a lone pair is going to donate into the carbonyl. So why is that anhydride so electrophilic?
Since it has to share the electrons with both sides, it's half the time it's going to leave for one less.
Right, so in the ester, those electrons on oxygen only have one place to go, right? They're only conjugated with that one pi bond we want to be reactive as an electrophile. Right? This oxygen, the electrons are divided between the 2 carbonyls. Right? And so because they have to divide their time, it's not going to affect, that one pair is not going to affect the carbonyl carbon as much, right? Because they're going to be spending half of their time in the other carbonyl carbon. Right? So as a result, that's going to be much more electrophilic than aldehydes, ketones, and esters, right? Just because that electron pair has to divide its time. Any questions about anhydrides? Everybody can rationalize why they would be more electrophilic? Yep, okay. Acid chlorides, of these, the acid chlorides are the hottest electrophilics, right? The most useful of these functional groups. We can make any of the other carboxylic acid derivatives directly from acid chlorides, right? Why are acid chlorides so electrophilic? One of the reasons we said already, right? Because the chloride is a nice stable leaving group. Right, so most nucleophiles that we add are going to be less stable than this leaving group. Right, but if you think about just the carbonyl, right, ignoring the nucleophiles for now, why would that carbonyl be electrophilic? Chlorine has 3 non-bonding pairs of electrons, right? So we should be able to put some electron density into that carbonyl carbon.
Chlorine is highly electronegative, and at the same time, it's like a big atom there that destabilizes the system because it will have all the electrons.
Great, yeah, so chlorine is going to be electronegative. Chlorine and oxygen are around the same electronegativity, right? So because chlorine is electronegative, there's going to be a lot of inductive pull away from that carbon, right? Making it electrophilic. The other thing that we have to pay attention to is the position of chlorine on the periodic table. So what row is chlorine in on the periodic table?
Halogens, the second last.
That's the column, right? So it's in the halogen column. Which row across? Which shell are the lone pair electrons in chlorine?
It's in the third row.
It's in the third row, right? So when X is oxygen or nitrogen, right, that p orbital is going to be a 2p orbital, and it's going to overlap with this pi antibonding orbital, which is about the same size. Right? So you have this really good orbital overlap. You have these orbitals that are about the same size overlapping. Whenever this is chlorine, what is that p orbital going to look like?
It's gonna get bigger.
It's going to get a lot bigger, right? And so when this is 2p, we'll say it's that big. It's 3p, right? We have an extra shell, right? Now it's this big. That 3p orbital is not going to be able to overlap as well with the pi star orbital, right? Because it's like a Andre the Giant's hand shaking a baby's hand, right? It's just not a very good fit, right? So these orbitals have to, in order to get good effective overlap, they have to be equivalent in size. Right, so even though we draw chlorine, or we can draw chlorine with 3 non-bonding pairs, right, because those non-bonding pairs are in such a big orbital, they're not going to be able to overlap as well with the pi system. So conjugation is going to be, I don't want to say minimized, but it's going to be greatly reduced in chlorine compared to oxygen or compared to nitrogen. Any questions about this? So I'm biased. I think this is really cool, right? Because what we did was we explained this whole spectrum of reactivity based upon first principles that we learned in the first few weeks of this class, right? We were looking at understanding hybridization, shape of molecules, understanding where electrons are, right? Understanding how orbitals can overlap. Right? And that's really the basis of this class, applying those first 6 chapters to different systems to help us understand those systems. Yeah.
Just to make sure that I'm understanding, so the acid chloride is more, has more relative electrophilicity than the acid anhydride because it has that 3p, so it's unable to hyperconjugate.
Yeah, so it's not hyperconjugation, it's just regular conjugation.
Or regular conjugation.
Yeah, so the electrons that would stabilize the pi antibonding orbital or stabilize the system, right, because this orbital is so big, can effectively overlap with the pi antibonding orbital. Right, and so where we see stabilization of the carbonyl from electron donation here, right, electron donation here, electron donation there, we have electrons on chlorine, but because that orbital is so big, we don't get a whole lot of electron donation. Okay, we still have a little bit, right? We still have the conjugation. Other questions? Yeah, Rachel.
I'm still confused about the difference between the hyperconjugation and the high conjugation contributing to the overall electrophilicity, because in our example from Wednesday, when we compared ketones to esters, the ketone hyperconjugates, and we said that was more stable.
More stable
than the ester, which is going to be high conjugated, but today you said the high conjugated contributes more to the.
Yeah, so the ketone is more reactive, higher energy, more electrophilic than the ester. Right, so, yeah, and I thought I had said the same thing the other day, but I might have misspoke. Right, so if the ketone is more electrophilic than the ester, and the ketone has 2 elements of hyperconjugation, right, the ester has only 1, and then 1 element of conjugation, what that means is that the formal conjugation is going to reduce the electrophilicity more cleans things up a bit. Other questions?
So aldehyde also only has one element of hyperconjugation, so why is ketone less reactive than it if ester also only has one element of hyperconjugation?
So aldehydes are going to be more reactive. So remember that like these things make the molecule less electrophilic, right? So any element of hyperconjugation or any element of formal conjugation is going to reduce the electrophilicity, right? So here we have one element of hyperconjugation, right? Here we have two elements of hyperconjugation, right? So less reactive. Here we have one element of hyperconjugation and one element of formal pi electron conjugation, right? So that's even less reactive, right? Same thing here, but now we have a nucleus that's less electronegative than the oxygen, so pi conjugation is going to be greater, or electron donation into the pi system is greater.
Okay, thank you.
Other questions? All right, so since acid chlorides are going to be, of these, the most versatile, it's actually important to know how to make them. Right, and so this will give us options. Planning out syntheses. Okay, so here's a reaction scheme that's showing synthesis of an acid chloride from an acid, or sorry, from a carboxylic acid. Right. In terms of reagents, there's really only one reagent. Right. We can run this reaction in a couple of different ways, but we're just going to look at this one condition. Right. Reagent is called thionyl chloride, so it's a tetrahedral sulfur, 2 chlorine atoms, and then a double bond to oxygen. Right, and then we're going to use dichloromethane to run this reaction as a solvent to run this reaction. Right? So it's not participating in the mechanism of the reaction, right? Just bringing everything together in solution. We could use other solvents for this, so we could use THF, we could use toluene. Right? I just chose dichloromethane because it's a pretty common solvent for this reaction. So let's go through the mechanism of this. Right? My mechanism is going to be slightly different from the mechanism that you see in the book. Right? Both they're more or less the same. Right? I'm just drawing my arrows a little bit differently. Right? But in effect, they're the same mechanism. Right? So I'm going to start by reacting my carboxylic acid with thionyl chloride. Right, and this is going to happen through a substitution. So what I'm going to do is I'm going to take this oxygen with the hydrogen, make a pi bond, make a new pi bond to the carbonyl, right, and then use the pi electrons from the other oxygen to add the sulfur, and we're kicking out the chloride. Any questions about this? Yeah.
So the arrow breaking the thionyl chloride, right? The
Yeah.
chlorine bond, are the electrons just going to the chlorine atom, or are they just like?
They're going to the chlorine atom.
Okay.
Yeah, so, yeah. Usually if it's a leaving group, often I'll just show the arrow going out, so I'm sloppy, but yeah, you're right, technically, so the arrow should point to the chloride. Yeah.
Is there a reason why the sulfur's coming off the oxygen and didn't just attach to the carbonyl? Like usually, you know how.
Because that's what the arrows are showing us, right? So if we're making a new pi bond from this oxygen to this carbon, right? This carbon already has 8 electrons around it, right? So if we're pushing a new pi bond into that carbon, then a pair of these electrons has to leave from carbon, but they stay with oxygen, right? So you can imagine them kind of flipping up like this and just grabbing onto the sulfur.
Okay.
All right, and then the third arrow shows the chloride. Make sense?
Yeah.
Right, so we haven't gone over too many mechanisms like this where we're showing 3 or more arrows in one step, right? So this is somewhat new. Yeah, Julie.
Would I be correct that it was fairly high energy, to have?
This intermediate?
Yeah.
Yeah, I would say that's a pretty high energy intermediate. Yeah. So looking at any other questions? Okay, so looking at what we're making, right? And what we have in this intermediate, what's the next step going to be? Right, thinking about the bonds that need to be made, bonds that need to be broken, groups that have to be lost. What's a rational next step? Yeah.
Keep running
Here, we're gonna keep that proton there actually. So kinetically, so you're right. So kinetically, that'd be a really fast thing to do, and that's probably going to happen, but it's not going to get us. Unfortunately, it's not going to get us to the end, right? Yeah. So you're trying to use chloride to pull the proton. Where does that chloride end up in the product? Joey?
Attach it to the carbonyl carbon.
Yeah, it's attached to the carbonyl carbon, right? So, right, you can see the huge difference between the starting material and the product is that in the product we have this carbon-chlorine bond, and that has to be made at some point during the mechanism, right? Here, right, we have a chloride, Cl-, so it's a nucleophilic chlorine, okay? And everybody hopefully can recognize this as a activated carbonyl, so a really good electrophile. So at this point, it hopefully makes sense that the nucleophilic chloride can add to that carbon so we can make that carbon-chlorine bond in this step. And then we would put those electrons on to oxygen. So this is going to be the second intermediate in the reaction. All right, and then to get to the product, hopefully you can see which atoms need to stay together and which atoms need to leave, right? So we need to get rid of, obviously, this oxygen, the sulfur, this oxygen, the chlorine, and the proton, right? And in this state, this intermediate is basically going to kind of break apart into 3 different pieces. So we are going to take these sigma electrons between oxygen and hydrogen, and we're going to make a new pi bond, right? That's going to be the pi bond on the acid chloride, carbon-oxygen pi bond on the acid chloride. Okay. At the same time, right? What we essentially did was we activated one of the oxygens of the carboxylic acid, right? Using this sulfur. So we made that into a good leaving group with the thionyl chloride. And so we're going to get the second oxygen to leave, to be pushed out, right? Those electrons are going to form a new pi bond between sulfur and oxygen. Right? And then the third arrow that we draw is going to be start with the sulfur chlorine sigma electrons and attach to the hydrogen, or attach to the proton. All right, so if you look at this, we have 6 electrons moving around in a 6-membered ring. What does that remind you of?
See,
Is that? Did you say something?
I said benzene.
You said benzene. Good, yeah. So, right? It reminds you of an aromatic system. 6 electrons moving cyclically in a 6-membered ring. Right? So this step is actually very favorable because you get this aromatic-like transition state, right? Where you have these 6 electrons moving around in a 6-membered ring. Right? And when this is all said and done, the 3 products that we have are going to be the acid chloride, SO2 gas, and then hydrogen chloride. Okay, both SO2 and hydrogen chloride are gases or can lead the reaction, so we're basically just left with the acid chloride.
So could you say they're conjugated?
What do you mean? So because this is aromatic, is that? Yeah, we can't go that far. We would say it's an aromatic-like transition state, but yeah, it's not complicated. Okay, questions about that? I think we'll just stop there. So that will actually take us to the end of chapter 9. Chapters 8, 9, and 10 are all carbonyl chemistry. Chapter 8 is aldehydes and ketones. Chapter 9 is these carboxylic acid derivatives. Chapter 10, what it does is we take all of those carbonyls and we look at a fresh set of nucleophiles. We're looking at hydrogen and carbon nucleophiles. Right, so we'll start in chapter 10 on Monday. More of the same thing with an exam schedule for next week. Obviously, we're not going to get through the material needed for that exam, so it's going to be pushed back till after next week. Unless you want to take one next week.